The rules of locomotive engineering were not suggestions. They were written in physics, in metallurgy, in the accumulated wreckage of machines that pushed too far and failed. One boiler per frame. Pistons turn the wheels. Steam exhausts backward, not forward. The engineers who built the world's railways believed these rules existed because nature demanded them. Then came the machines on this list. Each one ignored a rule the profession considered unbreakable. Each one ran anyway. Here are 10 unusual locomotives engineers said were impossible. Number 10, Pennsylvania Railroad S2. Steam turbine locomotive. This was the first steam locomotive delivered to a major American railroad with no cylinders, no crossheads, and no connecting rods. Every steam engine since the 1820s converted reciprocating piston motion into rotary wheel motion through a mechanical linkage that filled the locomotive's flanks with rods, valves, and crossheads. The S2 eliminated all of it. Baldwin Locomotive Works delivered the sole prototype to the Pennsylvania Railroad in 1944, built around a direct drive steam turbine coupled to the driving axles through reduction gearing. The forward turbine produced approximately 6,900 horsepower. The wheel arrangement, 686, had never existed before and never would again. The added leading and trailing axles required by the extra weight of heavier wartime construction. In testing, the S2 ran with a smoothness no reciprocating steam locomotive could match at speed. The vibration that defined conventional steam operation was simply absent. But fuel and water consumption in low-speed service was catastrophically uneconomical, and the turbine was sensitive to dirt and debris in a way that railway operating conditions punished mercilessly. The S2 was retired in 1949 and scrapped. No buyer. No preservation effort. One of the most technically advanced dead ends in American steam history, and not a trace of it survives. Number 9. Soviet AA-20 steam electric locomotive. In 1939, Soviet engineers at the Kolomna Locomotive Works began construction on a machine that challenged the fundamental assumption of how a steam locomotive moves itself. The AA-20 interposed a complete electrical system between its boiler and its wheels. Steam drove a turbo generator. The generator powered traction motors on the axles. It was a steam locomotive that propelled itself electrically, a concept Soviet engineers pursued independently from Western experiments, on a frame approximately 38 meters long with its tender rated at approximately 3,600 horsepower. The logic was sound. Electric drive could distribute tractive effort across more powered axles than direct steam transmission allowed, which Soviet planners needed for heavy freight over long grades. The AA-20 completed operational trials on Soviet mainlines in the early 1940s, demonstrating that steam-electric transmission functioned in genuine service conditions. World War II priorities redirected resources before the concept could develop further. The sole prototype was withdrawn and never preserved. Its existence is documented in Soviet railway technical literature, and almost nowhere else. Steam-electric drive worked on Soviet track. The war simply had other requirements for the steel. Number 8. Great Northern Railway W1 class electric locomotive. Railway operators had a problem in the Cascade Mountains of the American Northwest. The grades demanded more tractive effort than any single electric locomotive frame could deliver. General Electric's answer, delivered to the Great Northern Railway in 1947, was a machine so unconventional that engineers across the country studied it with open skepticism. The W1 used two complete locomotive bodies sharing a single articulated frame with a wheel arrangement, 1B plus D plus D plus B1, that had never appeared on an American locomotive and never would again. Each unit stretched approximately 101 feet and weighed approximately 517,000 pounds. Continuous output reached 5,000 horsepower. Starting tractive effort reached 180,000 pounds. In Cascade Tunnel service, a single W1 replaced multiple conventional electric units on the steepest grades, delivering figures no previous American electric locomotive had approached. Only 2 units were built. Both were retired when Great Northern dieselized its mountain electrification in 1956. One was acquired by another railroad for experimental use before scrapping. Neither survived. The W1 was too large, too specialized, and too expensive to have a future anywhere, and also the most powerful electric locomotive America had ever built. Number 7. Chesapeake and Ohio, M1 steam turbine electric. The rule of steam locomotive design held that coal heated water, water became steam, and steam pushed pistons. That chain had been reliable for a century. The C&O M1 severed every link in it. Baldwin Locomotive Works and Westinghouse Electric delivered 3 units between 1947 and 1948, numbered 500 through 502, each measuring over 154 feet, with its tender and weighing approximately 856,000 pounds for the locomotive alone. The boiler operated at 310 pounds per square inch, driving a turbine, which drove a generator, which powered traction motors. No pistons, no main rods. No direct mechanical connection between boiler and wheels. Rated output was 6,000 horsepower per unit. The C&O intended them for passenger service between Washington and Cincinnati. They entered service and were withdrawn within 3 years. Coal and water consumption was extraordinary. The turbine electric drive system was unreliable. Railroad workers called them sacred cows, expensive, immovable in any practical sense, and producing little useful work. All 3 were scrapped by the early 1950s. The M1 confirmed 2 things simultaneously. Turbine electric drive was a sound concept, and coal-fired steam was the wrong way to power it. Number 6. New York Central M497, the Black Beetle. How do you test whether existing American rail corridors could support high-speed service when conventional diesel equipment tops out far below the required speeds, and purpose-built high-speed trains cost millions and years of development? In the summer of 1966, the New York Central answered that question by bolting 2 surplus jet engines from a Cold War-era bomber onto the roof of a standard commuter rail car and pointing it down a straight section of unmodified existing track. Project engineer Don Wetzel and his team at NYC's Technical Research Center completed the conversion in 30 days. The base vehicle was a Budd RDC-3 self-propelled railcar. The engines were 2 General Electric J47-19 turbojets, surplus from a Convair B-36 Peacemaker. Wetzel's wife Ruth, a commercial artist, designed the streamlined fiberglass nose cone. On July 23, 1966, with Wetzel at the controls and NYC President Alfred Perlman in the co-pilot seat, the M497 was officially clocked at 183.85 miles per hour on a 21-mile straight. Wetzel later stated the speedometer had peaked at 196 miles per hour before he reduced power. The entire project cost a fraction of conventional high-speed rail development. The NYC-Pennsylvania Railroad merger made the data irrelevant. The jet engines were removed. The railcar returned to commuter service and was scrapped in 1984. A commemorative plaque marks the site in Bryan, Ohio. The Black Beetle proved that existing American track could handle speeds the industry said required decades of infrastructure investment to reach. Number 5. Union Pacific Gas Turbine Electric, the Big Blow. This was a locomotive that burned fuel nobody else would touch. While every other American railroad was standardizing on diesel in the post-war era, Union Pacific was operating the largest fleet of gas turbine electric locomotives in the world, burning Bunker C heavy fuel oil, a petroleum residue so viscous it had the consistency of roofing tar at room temperature. A worker pressing a hand into unheated Bunker C would watch the impression close over the course of several minutes. It had to be heated to 200 degrees Fahrenheit before it could be pumped into the turbine. General Electric delivered 55 gas turbine electric locomotives to Union Pacific across 3 generations between 1948 and 1961. The third-generation super turbines produced 8,500 horsepower per set, the most powerful single-unit locomotives in the world at the time. The turbine exhaust was so loud that railroad crews could hear one coming from miles away, which is where the nickname came from. At their operational peak, Union Pacific's turbines handled approximately 10% of the railroad's total freight traffic. Rising fuel costs and improving diesel technology ended the experiment. The fleet was retired between 1963 and 1970. One third-generation unit survives at the Illinois Railway Museum. The big blow ran on fuel nobody else wanted, made noise nobody could ignore, and moved freight nothing else could match. Number 4. British Rail Class 55 Deltic. The rule of diesel locomotive engineering said a railway diesel engine was designed from the ground up for railway service. Heavy, 4-stroke, robust, built to withstand decades of hard use in a controlled car body environment. Napier and Son had built the Deltic engine for fast Royal Navy patrol boats. English Electric adapted it for railway use. Each Class 55 locomotive contained two Napier Deltic D18-25 opposed piston 2-stroke diesel engines, a triangular arrangement of 3 crankshafts and 6 banks of cylinders per engine, with 36 pistons per locomotive and no cylinder heads, because in an opposed piston layout, pistons move toward each other, and the combustion space needs none. Combined output was 3,300 horsepower. No conventional British diesel of the era came close on a weight-for-weight basis. 22 units were built at the Vulcan Foundry between 1961 and 1962, assigned to the East Coast Main Line between London King's Cross and Edinburgh. For 21 years, the Deltics hauled the heaviest named expresses on that route at sustained speeds no other British diesel could maintain. They were replaced in 1982 by the Intercity 125 high-speed trains. 6 have been preserved. Several remain operational on heritage railways. The Deltic put a Marine combat engine into an express passenger locomotive and kept it there for 2 decades, which the rulebook said was impossible, and the timetable said was essential. Number 3. Pennsylvania Railroad T1 duplex. Railway engineers had a problem. Achieving sustained 100-mile-per-hour performance with heavy passenger trains required either more driving wheels on a longer rigid frame or articulation, neither of which the Pennsylvania Railroad wanted for its premier express services. Their answer split the driving wheels into 2 independent groups on a single rigid frame, powered by 4 cylinders instead of 2. Baldwin Locomotive Works produced 2 prototypes in 1942 and 50 production units in 1945 and 46. Industrial designer Raymond Loewy styled the production locomotives with a shark nose profile unlike anything else on American rails. In testing, the T1 produced 6,552 horsepower, 46% more than a comparable conventional locomotive of equivalent weight on drivers. Prototypes routinely held 100 miles per hour with 13 or more passenger cars between Harrisburg and Chicago. The duplex arrangement had a fatal weakness. Each driving group carried less adhesion weight than a conventional locomotive, making the T1 violently prone to wheel slip at both low and high speeds. The complex valve gear was nearly inaccessible for maintenance. By 1952, every T1 was out of service. All 52 were scrapped by 1956. The T1 Trust nonprofit is currently constructing a brand new example, number 5,550, from scratch. Not one original survivor exists. Number 2, Norfolk and Western Y6B compound articulated. Conventional wisdom in 1948 was unambiguous. Steam was finished. Every major American railroad was buying diesel locomotives. The steam era had ended, and engineers still arguing otherwise were simply wrong. Norfolk and Western's Roanoke shops completed their last Y6B in 1952. They built it anyway. The Y6B was a 2882 compound articulated locomotive, two sets of 8 driving wheels on a single articulated frame. Steam used twice before exhausting. First, through high-pressure cylinders, then through larger low-pressure cylinders to extract every remaining unit of work from each pound of coal burned. Starting tractive effort in simple expansion mode reached 152,206 pounds, placing the Y6B among the most powerful steam freight locomotives ever to operate in regular service anywhere on Earth. Norfolk and Western built these machines because their own engineering analysis said steam was still the right answer. Cheap coal from their own online traffic. Expert shop forces. A physical plant designed entirely around steam operations. The Y6B fleet hauled loaded coal trains over Appalachian grades until 1960, outlasting steam on virtually every other American Class 1 railroad. Several examples have been preserved. The most prominent is displayed at the Virginia Museum of Transportation in Roanoke. The Y6B didn't argue with the rule that said steam was finished. It just kept working while everyone else accepted it. Number 1. Southern Pacific Cab Forward AC-12. Every steam locomotive in the world puts the cab at the rear of the boiler. The crew stands behind the firebox, behind the boiler barrel, behind the smoke box. That arrangement is not tradition for its own sake. It is the direct consequence of how a steam locomotive is assembled, with the tender following the boiler and the cab sitting at the junction between them. Southern Pacific's main line over the Sierra Nevada passed through nearly 40 miles of snowsheds and 39 tunnels. In a conventional locomotive, exhaust gases pushed back into the cab in those enclosed spaces. Crews were suffocated. One desperate engineer ran his locomotive backwards through a tunnel so the smoke would trail behind him instead of engulfing him. Southern Pacific looked at that improvisation and built 256 locomotives around it. The cab forward was a conventional articulated locomotive running in reverse. Crew at the front, stack behind them, tender trailing at the rear, oil fuel piped from the tender through the full length of the locomotive to the firebox at the front. A person of average height standing beside an AC-12 at a station reached approximately to the bottom of the cab windows, the cab floor level with the top of a standard door frame. The fuel line running from rear tender to front firebox was longer than most residential city lots. Baldwin Locomotive Works built the final and most powerful series, the AC-12 class, in 1943 and 1944. 20 units, numbered 4,275 through 4,294, weighing over 1 million pounds with their tenders, capable of 70 miles per hour, hauling both heavy freight and express passenger trains over the same grades where crews had once been suffocated. Number 4,294, the last cab forward built and Southern Pacific's last new steam locomotive, is the sole survivor. It is preserved at the California State Railroad Museum in Sacramento. It exists because one engineer, facing death in a tunnel, turned his locomotive around, and a railroad decided that was the right answer for 50 years. Every machine on this list existed because an engineer looked at a rule and asked what it was actually protecting. Sometimes the rule protected the crew. Sometimes it protected a budget. Sometimes it turned out the rule was protecting nothing except the comfort of not thinking differently. The machines that changed railway history were never the ones that accepted the answer they were given. If you want to see more, click the video on screen now.